Hi everyone, this is Maths for Uni. This is question 1F from MAT 2019. If you find this content helpful, then please consider liking and subscribing, as well as checking out our Udemy course, of which the link is in the description. The question says, in the interval 0 less than or equal to x less than 360 degrees, the equation sine cubed of x plus cos squared of x equals 0 has A 0, B 1, C 2, D 3, or E 4 solutions. So if we start by looking at our equation, which is sine cubed of x plus cos squared of x equals 0, if we want to solve this equation, then it would be helpful to get it in terms of one type or the other of the trigonometric functions, either all in terms of sine or all in terms of cos. Here we can use the fact that sine squared of x plus cos squared of x is always equal to 1, and this allows us to write cos squared of x as 1 minus sine squared of x. If we insert this into the above equation, then we get sine cubed of x plus 1 minus sine squared of x is equal to 0, which is an equation purely in terms of sine. Next, we note that this is kind of a hidden cubic. If we write y as sine of x, then the equation becomes y cubed minus y squared plus 1 equals 0. We can first work out how many roots this equation has, and then turn those roots into roots for x instead of y. We use a similar procedure to that we used in question 1a, i.e. we write the cubic on the left-hand side as a function f of y, so this defines our f of y, and then we find the turning points of this function. So we have f prime of y, which means we're differentiating with respect to y, is equal to 3y squared minus 2y, which is 0 when y equals 0 and y equals 2/3 by factorising. Then we should calculate the value of the function f at these turning points. So when y equals 0, we have f of 0 is equal to 1, and when y is 2/3, we have 2/3 all cubed minus 2/3 all squared plus 1, and if we work this out, we get 23 over 27, and in particular, it's important that these values are both positive. Using this information, we can start to plot f of y as a function of y. So we have our y and our f of y, and the function must look something like this, where we have our turning points here at 0 and here at 2/3. Because the turning points both occur above the horizontal axis, we know that there is only one real root, which is somewhere here. However, remember that y is equal to sine of x, and so if we are to solve our original equation for x, then we would need any roots to lie between -1 and 1 for them to give roots in terms of x. So it's worth trying to figure out where this root here lies in terms of y. We know that when y is 0, we have a value above the horizontal axis. If we look at, for example, y is minus 1, then we have f of minus 1 is minus 1 cubed minus minus 1 squared plus 1, which is minus 1. And this is underneath the horizontal axis. So wherever minus 1 lies, let's say it's here, it must be on the left-hand side of the root because it has a negative value of minus 1. As such, we can indeed say that our root for f of y lies in our desired range between 1 and minus 1. In particular, it does not lie exactly at the value minus 1 because the function is not 0 at that value. Now, just because there is only one real root for y, this does not mean that there is exactly one real root for x. Recall that x is in the range between 0 including 0 and not including 360 degrees. If we draw y in terms of x, remembering that y is sine of x in this range, then it would look something like this, where 180 degrees is here, 360 is here, and we can label our axes as x and y. Recall that in terms of y, the root lies between minus 1 and 0. If we plot on minus 1 that occurs at the minimum and 1 that occurs at the maximum, the root occurs somewhere in here. It's definitely negative, but it does not go past minus 1. Therefore, we can use this graph to find out how many roots lie inside this range. We see that there are exactly 2 roots in this range, and therefore the answer is C. If our range was slightly different, however, then we may have gotten a different answer. For example, if there were no range, then there would be infinitely many roots for x, because sine of x would extend off to infinity in both directions, and would hit this negative line in infinitely many places. If you found this content helpful, then please consider liking and subscribing, as well as checking out our Udemy course, of which the link is in the description. Thanks for watching, and goodbye for now.